So I will be the session chair for this evening for the keynote speaker for both Hikmet and also Professor Nazir. But first of all, I would like to greet all of you for ISSA 2020. I know you miss the hotel scenario or environment, but still you can bring this computer to the hotel and you can feel the hotel. And I think you miss the lovely food, but now I think your wife cooking also very good. Yeah. So before we go for the next section, which is keynote, I would like to greet to all. So before that, I will introduce Professor Hikmet, the biodata before his speech. So, okay, Professor Hikmet was born in 1959. He graduated from Untitled University, the Department of Mechanical Engineering in 1980. He received his master degree in Mechanical Engineering from Universiti Technical University of Istanbul in 1982. He received his PhD degree from Anadolu University in Eskisehir in 1987, and he started his full-time teaching job at Anadolu University. And after that, he became an assistant professor and associate professor in 1988 and 1992. And he received full professorship in 1997 from Anadolu University in Tahir. He was right about the research. He has a wide range of research interests, including the sustainable aviation, aircraft propulsion system, insulation, heating, ventilation, and air conditioning, and many more, including the indoor air quality, gas turbine, cogeneration system, renewable energy, energy economic fuel and combustion. Okay. He also served as chief editor-in-chief as a guest editor for international scientific journal. He published national and international papers over 300 and 400 books. He is an active member of Chamber of Mechanical Engineer and many sector associations, various international scientific organizations and society. Perhaps the topic that Prof. Hikmet will introduce this as a keynote this evening is quite related to our problem, which is the indoor air quality in aircraft and possible problem related to IAQ. So perhaps this topic will give some insight what happens to the aircraft and air inside it. So without further ado, I would like to call on Professor Hikmet to have his first keynote for the ISSA 2020. Thank you.
Thank you so much, Chair. Dear rectors, dear Chair, dear keynote speakers, dear guests, dear distinguished participants, welcome again to our symposium and this session. In this keynote speech, my presentation title is Indoor Air Quality in Aircraft and Possible Problems Related with Indoor Air Quality. My presentation contains indoor air quality, environmental control system in aircraft, factors influencing indoor air quality aircraft, problems caused by cabin atmosphere, application, global trade, COVID-19, and conclusion. Especially in passenger aircraft, comfort criteria and flight safety are a priority depending on the increasing demand process in this context. The manageability of indoor air quality, especially system components, has become valuable by international aviation organizations. The development of effective control system in indoor air management, pollutant control, and related filtration systems can be seen as important stages. However, recirculation air, reclamation, and fresh air mixtures in aircraft are continuing practice in modern aircraft and means that especially life-threatening pollutants are given back to the same environment. In international standards, CO2, CO, ozone, relative humidity, and temperature have been accepted as a basic parameters of indoor air comfort standards. The keys to clean air is include high rate of fresh air flow, high efficiency particulate air filters, commonly called HEPA filters, and design of aircraft airflow distribution. The biggest factor in cabin air quality is inflow of fresh air. Aviation regulatory authorities such as the Federal Aviation Administration and European Aviation Safety Agency require a minimum rate of 0.55 pounds per minute outside fresh air flow per occupant. In a large commercial passenger aircraft, that means a typical environmental control system may replace the air occupying the cabin every 2 or 3 minutes, minus 20 centigrade to 30 times per hour. By comparison, the general guidance of fresh air inflow for buildings is only 4 changes per hour. In this presentation, current environmental control systems have been briefly studied and the risks have been emphasized relating to air pollutants, health, comfort within the context of indoor air quality. Recently, the number of passengers who prefer traveling by aircraft has increased substantially. These passengers are people who probably suffer various ailments and are various age groups. Today's commercial aircrafts run different atmospheres, having different temperatures, pressures, and humidity changes. Aircraft cabins have indoor characteristics similar to those in houses and office buildings. But still, these cabins differ from other buildings in some respects, such as available space per person, pressurizing requirements, activity levels within the cabin. Passengers are exposed to atmospheric factors such as reduced air pressure, various air pollutants, ozone, carbon monoxide, and other organic chemicals and biological structures, and low humidity. Modern aircraft are equipped with environmental control systems to provide safe, healthy, comfortable flight conditions for both passengers and crew. In this system, outside air is taken from the power system of the aircraft and mixed with the filtered indoor air before being introduced into the cabin. ISSA has been designed to reduce the air pollutants can possibly enter the cabin and to control temperature, pressure, humidity, ventilation of the cabin air. The environment that today's aircraft travel in is not the atmosphere with physical conditions that people can live in without any protection. For this reason, rather complicated ACS systems are used in modern commercial aircraft. Environmental control systems have been designed to meet psychological needs of human beings in any flight condition and to provide defined comfort levels during the flight. The design of the cabin ventilation system is based on introducing ventilated air into a row of seats, collecting and discharging to the air from the same row. Such an approach essentially reduces the risk of spreading infections within the aircraft cabin. The environmental control system is the most important component of the passenger and flight team, providing a safe and healthy flight, especially in different environmental conditions. This system provides pressure balance and flight safety. Air distribution system is an important component of this structure. The environmental control system of the aircraft provides air supply, thermal control, and cabin pressurizing for the crew and passengers. Avionics cooling, smoke detection, and fire are also commonly considered part of the aircraft's environmental control system. The system providing effective distribution of the air in the cabin is differently conditioned for each part of the aircraft. The performance of distributed air is related with the air circulation coefficient. The minimum and maximum values of circulation coefficient are 10.4 and 26.4 respectively, depending on cabin type and capacity. Cabin air is renewed every 2 or 3 minutes. The use of HEPA filters and top to bottom air circulation ensure aircraft cabins continue to be safe environment for all passengers on board. Management of air conditions in cabin air conditioners, pollution parameters, and homogeneous air distribution are based on a multi-directional management infrastructure. Although the prediction of the standards is 50% for recirculated bleed air, this ratio can reach up to 80% in some applications. Thermal comfort must be managed with respect to the flow chart, which includes seasonal and altitude conditions. These parameters are a little bit different in the aircraft. In an example, the hot bleed air must be cooled off first. The directed air and chilled are sent to the heat exchanger. The bleed air is chilled in the expansion turbine. Then it is sent to distribution system after the relative humidity is controlled. Cabin ventilation has several optional features. This is the humidity, the envelope using a source of dry ventilation air to provide radiant heating and cooling the cabin space using appropriately thermal conditioned ventilation air as the envelope air supply to raise cabin humidity by preventing cabin air entering the envelope where it is moisture will condensate on the cold fuselage to protect against fire risk and to facilitate the energy saving potential of new aircraft ventilation ejector technology. Thermal comfort management should be seen as a very important issue. Simulations on this issue in the literature have shown that it is not possible to deposit a full homogeneous effect, especially when considering the passenger. For the passenger, a closer look at the local comfort rating shows that existing distribution infrastructure have some disadvantages for some body parts. The thermal comfort management of distribution systems is not fully realized, especially depending on the climate conditions. The comfort conditions must be taken into consideration for each passenger, but current system designs are far away from this point. The control of average speed and flow rate from the blowing duct gives very average comfort results. Mixing air rate is also determined over these average values. Thermal comfort conditions for summer and winter are determined accordingly. In general, the cabin temperature is set 29 centigrade as maximum. Different methods are used for cleaning of recirculated air, HEPA filter, active carbon, and cool plasma. The disturbance of duct have different structures. The current duct systems cause problems in order to meet thermal comfort conditions, especially for commercial flights. That's why it's need to manage local control structures along with IT architecture. Management of air conditions in air conditioners, pollution parameters, and homogeneous air distribution are based on the multi-directional management infrastructure. In existing control regulation, the cleaning of the return air with standard filtration is the primary concern, primarily when pressure and temperature control is the basis. In addition, it is very difficult to detect different pollutants via detecting pollution. It seems that the system configuration needs to be redirected in and an effective information architecture is needed. The occupancy rate and pollutant source, cabin and luggage load directly affect all parameters. In this context, the management algorithm should be considered in dynamic structure. Especially in strategy 1, it is important if the load calculations are changed depending on the aircraft, navigation process, and IT information technologies, architecture for dynamic management of cabin control conditions provide to be concentrated on the work control equipment, while providing effective management for direct comfort management. There are several factors in influencing indoor air quality in aircraft which can be classified into 5 categories: pressure, oxygen, humidity, air contaminants. Inadequate fresh air, instant changes in the levels or interaction between these factors can cause deterioration of indoor air quality and consequently negative effects on the health of both passengers and crew. This condition makes it more inefficient to fly at higher altitudes. For this reason, almost all commercial aircraft cabins are pressurized for safety of both the crew and passengers. Pressure. Even though the cabin pressure is intended to be held constant at 2,450 meters, this level of pressure is lower than that at sea level. This level pressure has some negative effects on psychology of passengers. The reduced pressure causes expansion of the air trapped in body cells and creates some minor sicknesses, while in sensitive metabolisms, it can cause more serious health risks. When the partial pressure of oxygen is lower than that level, ingress of oxygen to the blood is reduced and the usual rhythm of body fails. In general, the temperature of cabin is taken not as health issues, but mostly as a comfort issue. However, it can cause health problems together with other psychological and biological factors. Temperature affects the liquid loss of the passenger and the crew. Furthermore, the humidity, this is directly related with temperature, also affects thermal comfort. As is well known, high temperature and low humidity cause sick building syndrome. Sick building syndrome reveals itself as exhaustion, headache, irritation of the skin, and mucous membrane, all acute symptoms. It is widely known that temperature affects health and air quality indirectly. Since people show a tendency to be less active in higher temperatures, the risk of deep vein thrombosis is affected by cabin temperature. A combination of temperature and humidity can affect the viability of airborne pathogens and the immune system of body against diseases. Relative humidity of cabin air has two significant characteristics with regard to indoor air quality: passenger comfort and aircraft structure and safety, particularly in high temperatures. Relative humidity in the aircraft cabin, when it is higher than 70%, creates a displacing environment for passengers. In this situation, condensation occurs in the cabin and water droplets can cause corrosion that is harmful to the aircraft structure. Temperature affects health and air quality indirectly. The effects of jet lag with high temperature are fatigue and reduced alertness, concentration, impairment of mental performance, including memory loss, digestion problems. Enhanced ECS systems in today's modern aircraft dry the air taken from outside using moisture separators. Thus, the main source of the humidity in the cabin is the respiration of passengers and evaporation from the human body. By mixing outside air and recirculated of air from the cabin, a relative humidity approximately 10 to 20% is achieved. In many aircraft cabins, depending on the aircraft type, the humidity varies between 15% and 19%. Lower humidity can cause drying of body surface, mucous membrane and skin, and irritation in eyes. Drying in mucous membrane and eyes particularly causes the eyes to become watery and painful. Lower humidity can seriously affect people who suffer from asthma, respiratory illness, and tracer disease. Little is known about the environment in which aircraft passenger cabins are under routine flight conditions, and what is known is limited in scope. However, it should not be forgotten that there is a systematic relationship between the source strength of the pollutants, physical factors such as ventilation rates, and operating modes, occupancy loads, and activities. Although there is not enough information about these contaminants, they are known to be potentially dangerous or cause acute irritation. However, based on the literature, it can be said that ozone, cosmic radiation, ground smoke, tobacco smoke, and carbon monoxide, biological aerosols, relative humidity, cabin pressure, carbon dioxide, volatile organic chemicals, and pesticides can be evaluated within this scope. It is related easy to estimate dose equivalent exposure for the person during flight process. Another pollutants for aircraft cabins are air aerosols. In this context, studies based on the characterization of indoor aerosols in the cabin are also seen in the literature in recent years. Ultrafine particle concentrations, especially in aircraft cabin environments, can be considered in this context. Ultrafine particles, aerodynamic diameter less than 100 nanometer, have correlated with the morbidity and mortality from respiratory and cardiovascular diseases due to extremely small size and large total surface area, which were more likely to carry harmful substances such as heavy metals or gaseous pollutants into the alveoli and blood. According to examples in the literature, the UFP concentration variation in real flight measurements are shown in that figure. The data showed that UFP concentrations in cabin air first dropped from the taxi to the cruise phase and then gradually increased for the remainder of the flight time. The main threat in the cabin, exhaling of carbon dioxide produced by the passengers and crew members regarding their metabolisms. The occupancy rate is the most affected parameter of carbon dioxide concentration. Researchers indicated that the carbon dioxide concentrations in return air decreases firstly, then kept steady, and finally increased in general during the whole flights, possibly affected by the adjustable outside airflow rate. Variations of carbon dioxide concentration and outside airflow rates in the aircraft cabin were comparable. However, it is seen in instances where it generally exceeds 1000 ppm during flight stages, which can be attributed to the lower outside airflow velocity. Ventilation air introduced to the cabin is taken from outside the aircraft, so any pollutant can enter the passenger cabin. Most airports are situated near the big cities, which often have significant air pollutant problems. Furthermore, exhaust emissions at airport are also another pollution source. During aircraft landings, exhaust gases and vapors from de-icing chemicals entering through the open doors can form the serious risk to health. Another threat is NOx, SOx emissions of the jet fuel carried to the cabin via bleed air. These gases cause irritation on lung tissue. Ozone is widespread, especially in summer, at altitudes of 40 degrees and above the altitudes of 9,000 meters. Ozone enters the motor via feeding air and causes acute and chronic diseases related with respiration. Additional threats, particle substances are caused due to the clothing and goods loading process and runway activities. Since most flights are at high altitudes, pollutants in the outdoor air are at very low levels. At these high altitudes, the main pollutant source is ozone. Ozone causes respiratory problems, increases asthmatic complaints, and damages the body's immune system. Internal pollution sources. Pollution from internal sources is caused by viruses, bacterial organisms, and other microorganisms from crew and the passengers. The most important pollution source is carbon dioxide product by respiration. Many countries insist on elimination of these insects from aircraft that take off from countries where malaria and such like are prevalent. To protect the aircraft from insects and the like, various pesticides are used. These chemicals used unsatisfactorily can cause a risk to health. The air in passenger cabins is dry, with relative humidity of 10% as the flight progresses. Meanwhile, a portion of the cabin air with its ventilation components, very dry outside air plus filtered recirculated air, and humidity components passed from the cabin to behind the cabin insulation, drawn there through liner leaks and openings by stack pressures. Some of this air is not lost as useful ventilation air. However, all the air drawn there, loses its humidity prior to recirculation, depositing its moisture and condensation on the very cold fuselage behind the insulation. The airplane's cabin air is mostly cleaned by HEPA filtration. In this filtration, the amount of fresh air circulated through these filters and delivered to the passengers is 1/8 of the circulating amount, while removing almost 100% of the 0.3 micron and large particulates. Suspended air is circulated in the air. Highly controlled filtration is provided in cabin environments with filtration sensitive to high airflows. Air change depends on aircraft model and cabin features. Although there are different standards in this regard in the world, air exchange takes place 15 times in narrow body aircraft and 13 times in wide body aircraft. For flights take then approximately 15 hours. Hypoxia is now I will explain the problems caused by cabin atmosphere. One of them is hypoxia. Hypoxia is weakening of bodily functions is caused by shortage of oxygen and blood cells and tissues. The shortage of oxygen can be due to various causes. The main causes is the reduction of partial pressure of oxygen in lung cells as a result of reduction in the pressure of oxygen in the environment. Hypoxia may reveal definite symptoms, while sometimes there may be no symptoms. If hypoxia occurs with no symptoms, there is the worst situation for passengers. Since passengers cannot be aware of the reduction in their bodily functions, and the following effects can be experienced: slowing down in thinking and wrong calculations, weakening of the memory and longer response time, higher number of breaths and cyanosis, weakening in reasoning, coordination degradation in muscles. Deep vein thrombosis is a blood clot in deep veins of the leg, although it can occur in other parts of the body. The danger, however, is that part of the clot can break off and travel to the lung circulation, where it blocks one of the pulmonary arteries. The possible results are low oxygen levels in the blood, collapse, and even death. Studies focused on DVT have shown that this sickness occurs during long flights and particularly in older passengers. In long-distance air travel, it causes symptoms either in the first few hours just after takeoff or after days of the flights, on average 4 days later. DVT is generally dependent on factors such as lack of experience, cramp, seating position, dehydration, and pressure in the cabin. However, this illness is not only a risk in air travel, but also a risk in rail and road travel. Precautions and preventation of DVT. Moving the legs up and down and back and forth at regular intervals, walking in the cabin for 5 minutes every hour, and taking deep breaths. Not maintaining the same position in the seat when sleeping, frequently changing the lying down position. Drugs causing drowsiness signs and alcohol must not be used during the flight. Before and during the flight, beverages must be consumed frequently. Water loss resulting from sweating and breathing increases the risk of blood coagulation. Clothing worn should be loose and comfortable. In some long-distance flights, many complaints have been concerning infectious disease contracted by passengers and crew of aircraft. Many passengers are anxious about being infected by the nearby passengers or recirculated air in the cabin. It is clear that there is an increased risk of infection caused by viruses and pathogens on long-distance flights. The main source of infection transmission in aircraft cabins, contaminated water and food, airborne person-to-person infection, direct contact with people or body fluids. In the context of the study, the questionnaire form had been prepared for passenger and crew of various airlines in Turkey. A literature survey and questionnaire process is the first stage of this study. The second step will cover the various measurements that will be conducted in airlines operating in Turkey regarding indoor air quality. The results of this study and the values from readings will also be revealed during the second stage of the study. Indoor air temperature, humidity, vibration, noise, the level of the bacterial growth that can cause the transmission of infectious disease measured using sensors placed in various areas of the cabin. The International Air Transport Association demonstrated that the low incidence of in-flight COVID-19 transmission with the updated tale of published cases. Since the start of 2020, there have been 44 cases of COVID-19 reported in which transmission is thought to have been associated with the flight journey. Over the same period, some 1,002 billion passengers have traveled. The most important threat facing the world has directly affected the aviation industry, like all other industries. More than 4 decades after state and federal epidemics showed how easy viruses spread from person to person on airplanes. The novel coronavirus has decimed global aviation. Daily passenger screens are down 95%, according to the Transportation Security Administration. The potential of thus unexpected threat stemming from aviation-based activities remained very low with the measures taken. IATA made the explanation you see in the slide on this issue, and the case rate was found to be 3.7 per 100,000. All elements of the industry were negatively affected by the process. Airline companies were in very different situations before the COVID-19 crisis began. In particular, air transport is one of the sectors with the highest dispersion in productivity across firms and to a lesser extent in profitability. While the growth strategies were reviewed, many different measures were developed in this regard. Air is bled from the engines into the air management system where it is cooled and compressed, then expanded and delivered off the cabin. Cabin pressurization is derived from the bleed air pressure, with outflow valves and fuselage allowing pressure to escape, enabling pressure to increase as an aircraft flies higher and decreases as it flies lower. It is all maintained as delicately as possible to maximize passenger comfort. Vice President, the General Manager of Air Thermal Systems Honeywell, Tahir says. Received substantial number of complaints relating to the flight by passengers and crew. Crew contaminants, cleaning agents, hydraulic fluids, ozone. Psychological effects, fatigue, noise, passenger sitting too close together, jet lag. Cabin environment, pressure and humidity, airborne particulates. Future studies in this area will be helpful in establishing a desirable indoor air quality in aircraft, and these efforts will lead the preparation of indoor air quality standards of aircraft, particularly for long-distance flights. Indoor air quality meeting higher comfort needs and having no health or safety risks will be achieved. Thank you so much. I think you don't think to get on aircrafts after this presentation.
Okay. Thank you, Prof, for the very interesting speech for the keynote. I think it's really tally with the situation now. So, can you hear me, right, Prof?
Yes.
Okay. Yeah, it seems that you you might not hear me anything. So, all right. So maybe I have one question. I open the floor now, the screen now, for the participant to ask the question using mic directly, or you can check. I have several questions in the chat. I will wait for those who want to ask directly. Yeah, please. Is there anybody want to ask a question to about this?
Sure. Actually, I'm looking at some questions at chat box. I can choose and I can answer these questions.
Okay. Actually, I can ask from behalf. Okay. Putra, a research assistant at Budapest University and economic. He has a question. What is the effect of cabin air system on engine performance and fuel consumption? What is the situation with electric and unmanned aerial vehicle in this regard? Yeah, can you clear with the question, Prof? Or I want to repeat?
Okay. Actually, it would not be true to consider in cabin air management only in terms of air conditioning. This effect is important in terms of flight safety directly in the environmental control system. Actually, it is necessary system component for the aircraft to have the desired indoor pressure and to maintain the life forms of people or living things in comfortable conditions. However, this effect, which provides a heating purpose in terms of conditioning, is only about 2%. of the total load. I think this aspect can be neglected. Regarding electric vehicles, it is still a particularly problematic issue today in the current technology with R&D process. The air conditioning load has an effect on average in the range of 25-30% of the total load. This situation is unsustainable structure actually. In this context, further research and advanced technology are needed for the alternatives to air conditioning process regarding unmanned air vehicles. It is necessary to evaluate it and in terms of thermal management, which is a different matter. Thank you very much. This question.
Okay, hopefully that answer the question from Putra. I have another question from Dr. Izani Gires. We distribute what happens if such as a blended wing body? What are the strategies for bleed air? The question, yes.
I couldn't see the question. Who asked the question?
I think it's a question from Dr. Izani. Yes, for electric aircraft or aircraft with distributed propulsion such as blended wing, what are the strategies for bleed air?
You are asking the second question?
Yes, the second question, yeah.
What is the situation with electric and unmanned aerial vehicles?
All right, okay, perhaps that will answer.
Or other question. Actually, I couldn't see the question here. Who asked the question?
One of the colleagues from UPM, Dr. Izani. Dr. Izani, you are here. Maybe you can ask directly. Yeah.
Hi, Prof. Hikmet. How are you?
Fine, thank you, Izani.
Okay, yes. My question is, when it comes to aircraft that are of more electric configuration or entirely electric, what is the strategy for bleed air? This is similar to what Dr. Utku asked just now.
Okay.
And then more interestingly, for aircraft that have non-conventional fuselage configurations, what will be the design strategy for environmental control systems? Thank you.
Actually, it can be changed depending on the system or and depending on the aircraft type. Actually, I cannot exact think about this issue. I can send exact information by email.
Okay, Prof. We have another question. I think the question comes from the chat from Dr. Shahrul itself. What kind of filter that we are being used for filtering the air? Are they the same level standard with like mask that we are wearing?
Actually, mostly HEPA filters are using in the aircraft. I think it's problem the maintenance of the filters on date. Filters is making their duties, but maintenance in this issue very important. But mask can be useful. Thank you.
So perhaps we can have some sort of mask that put inside the filter and can replace like every flight, right?
And I'm seeing
disposable mask or this disposable filter, perhaps maybe the good one. I don't know.
Professor Azmin, actually, I am seeing another question.
Okay, yeah.
Ziya Sögüt.
Okay, how many years will possible to implement this fully throughout all the aviation companies around the world? This is from Haisha Sufia.
Hmm?
Okay. All right. Okay. Sorry. Maybe I. Okay. Okay. One of perhaps I go for this question first. For IAQ in aircraft, how do the crew who are always exposed themselves in aircraft environment for approximately 80 hours a month protect themselves from the hazard and effect of bad quality indoor air? Maybe they ask for the effect when the crew is long enough in the aircraft. Yeah. I, okay, Prof?
Hasya Sufia, right?
I think maybe we can ask, Hasia Sufia.
How many years will it possibly take implement this fully taught all aviation companies around the world?
Maybe she asked about this pandemic.
I am not sure. I cannot answer this question. How many years?
Yeah.
Depends on the air conditioning sectors, and many years perhaps.
Yeah. I think when the vaccines is already there, perhaps we can settle this part. But there is another question from Lim Chi Ho about the staff of crew inside the aircraft that exposed in the air inside for long hours. How to protect them from the hazard and effect of the bad quality indoor air? Maybe that ask. Maybe the passenger is only 8 hours or for 12, but the for the crew is, yeah. Is there any long-term effect for that?
Whose question?
Lim Chi Ho.
Lim Ho.
Yeah.
Yes, thank you for
Yes. Before
who are always exposed themselves in the aircraft environment 20 hours mount protect themselves for the quality indoor air. Themselves in aircraft. Actually, I couldn't answer this question. How they can protect themselves? I think it is a little bit doctors' problems. I can answer.
Okay, maybe I can ask a bit on according to this. Is there any long-term effect for the crew? If there is a many effect of the air quality inside the aircraft, how about the crew itself that will already work maybe 10 years? Is there any side effect because of air ventilation or air quality in the aircraft? Is there any case that like we expose in too long in chemical, but how about the air quality in the aircraft itself for the crew that work inside it? Is there any side effect for that?
Okay, thank you.
Okay.
I think there are the last question.
Yeah, sure. That's the last. Because we are running out of time. But perhaps that's the last question from the screen. Yeah.
You will read or I read?
No. That's actually my question. Is there any long-term effect for the crew itself because of the air quality? Because there's so many factors that affect the air quality inside the aircraft that, like your slide, perhaps is there any side effect or long-term effect for the crew that work inside the aircraft? For passenger, there is maybe 8 hours or 12 hours. But for the crew, is there any record for that air quality will affect the health of the crew?
Yes, actually, I gave some conferences at the cabin crew at Turkish Airlines staff. And after the conference, they said if they know this knowledge, they cannot want to work stuff at in the aircrafts. So a lot of people don't know whether they know they know or not. Some of people disease, but they don't know what is the reason of this. Perhaps this reason in the flight, or because some infections they can show 4 hours later, 1 day or 3 days later. So they don't know.
Okay.
And I show the question, scientists and researchers are still having trouble with defining the ideal conditions for healthy air, particularly indoor air quality in aircraft cabins. According to your experience and knowledge, what measures should be taken to improve indoor air quality in aircraft cabins through COVID-19 pandemics? Scientific data of air quality can describe the comfort weather conditions with all their components. In this context, there is a reference criterion. As for the trade, we must take this issue seriously today. This is because the gas emissions might put people at risk, particularly during COVID-19 pandemics. As scientists, we have to develop different approaches for improving air quality, especially indoor air system solutions or algorithms can be produced by using artificial intelligence techniques instead of traditional preferences. In this context, my team and I have been conducted research in improving indoor air quality in aircraft cabins. Actually, the main goal in these algorithms is to include removal of potential contaminants from the environment before they come to the risk of human exposure. It is also very critical to make clear decisions, to quick action and manage control system well. Perhaps some scientists wants to study this issue. We can make collaboration to make some research about this issue. If they write to my email, we can make we can write a project about this issue. Thank you very much.
Okay, Prof. I think that will be the last question. And if you have any question that you want to ask about the air quality, perhaps you can email and also contact Prof. I think the email is available. Thank you very nice. Thank you very much, Prof, for the presentation and also answer. And perhaps we are going to move into the next keynote speaker. Thank you very much, Prof.
Thank you so much.
Okay. All right.